Okay, so we continue. Question 6. So question 6, we have a compound wire which is made of copper as well as iron. So both of these wires have different length, and also they have different values for the Young's modulus. Okay, so we want to find, or rather let me say, the compound wire here. They are fused, by the way. It's like you get a copper wire and an iron wire, then you attach them. They make one compound wire. Now this wire is being pulled. Okay, it's being pulled, and then the total length is increased by 0.01 meters. Okay, so now we want to find this tension that is causing this increase in the length. So we want to find the tension which is applied to the compound wire, and also we want to find the extension of each wire. Okay, of course we know that the total length is going to increase, but the increase on each wire will not be equal. So we'll have an increase on the copper wire as well as an increase on the iron wire, and adding those two elongations are making up the 0.01 meters. Okay, then after finding that, we go ahead and express, or rather find, the ratio of the extensions of the two wires. Okay, so take a look at this diagram here. This is how they look. We have from L to M, that is the copper wire, and from M to N is our iron wire. Okay, so we also know that the total elongation is given as the elongation of the copper wire plus the elongation of the iron wire, okay, which is equal to 0.01 meters. All right, because we are told earlier on in the question that the elongation together, or rather the total elongation, is 0.01 meters. Okay, so again we note that we have this expression of Young's modulus equals force over area divided by that. All right, so from this expression we can obtain the expression for the elongation. Right, we make the changing length the subject of the formula, and we're going to find that the changing length is given as L times the force divided by the Young's modulus times the area. Okay, so you do that on your own, and yes, as you're solving, of course you have to change that expression. So I have changed mine here already. I've expressed the changing length of copper as well as the changing length of iron as LC times the F, because it is the same tension acting on the compound wire, the F. Therefore, I have the length of copper times the force divided by the Young's modulus of copper times the area of copper plus the length of iron times the force divided by the Young's modulus and the area, giving me F multiplied by LC over YC times A plus LI over YI times AY. Right? So notice here that all these expressions are simply the expressions for the change in length of copper and the change of in length of the iron wire respectively. Okay, so therefore we proceed and say the total change in length, which is 0.01, is equal to F times length of copper divided by Young's modulus times the area of copper plus the length of iron divided by the Young's modulus for iron times the area for iron. okay, giving me 0.01 equals the tension, because this force is the tension that we are looking for. Tension times 12.82 times 10 to the minus 6, and we're obtaining the value of T as 780 newtons. Okay, so I'm sure we know how to reach about this stage at this point. We proceed now. We want to find the extension in each wire, okay, the change in length for each wire. So let's look at the change in length of the copper wire. We have the change in length of copper wire equals the tension times the length over the Young's modulus times the area of the copper wire. Substituting the values, we are going to obtain the change in length of the copper wire as 6 millimeters. Okay, so this means that the copper wire is only stretched 6 millimeters. Then for the other one, the iron wire, it's simply going to be the original length minus the change in length of the copper wire, because that is the extension that is remaining there. So the change in the length of iron is going to be L minus the change in copper wire. Okay, so here, correction again. So for this one, it's supposed to be the change in length of the iron equals the change in length, which is the total change in length, minus the change in length of the copper wire. Okay, so it's supposed to look like this. So we have the total change in length minus the change in length of the copper wire, giving us 0.01 minus 0.006 meters, giving 4 millimeters as the stretch for the iron wire. Okay, so I hope, well, I'm sure you understand here at this point. Okay, so now to find the ratio, we know that the change in length for the copper wire is 6 millimeters, whereas that of the iron is only 4 millimeters. So we can see that the copper wire has been stretched more than the iron wire. Therefore, the ratio here of the extension of copper to the extension of iron is 1.5 to 1. Okay, 1.5 to 1. All right, so question 7. A solid weighs 237.5 grams in air and 12.5 grams in a liquid in which it is wholly submerged. The density of the liquid is 900 kg per square meters. Calculate the density of the solid. Okay. Also, the density of another liquid in which the same solid would float with 1/5 of its volume exposed above the surface, the liquid surface. Okay, so we want to find the density of the solid here. We know that the weight of this solid in air is 237.5 grams, and the weight of the solid in water, or rather in the liquid, is 12.5 grams. Okay, so from here, the buoyance force is given as the weight of the object in air minus the weight of the object in the liquid. Okay, so now we have the mass, which is 237.5 minus 12.5 grams times 9.8. Okay, so we have to convert this into kilograms, by the way, standard units. So we're going to have 225 grams times 9.8, which is the same as 225 times 10 to the minus 3 kgs times 9.8, giving us the buoyancy force as 2.205 newtons. All right, so we also know that the buoyancy force is given as the density times the area times G times the change in the height, or simply as the volume times the density. Okay, so since our buoyant force was found to be this value here, okay, we can substitute and say buoyant force therefore is going to be the density times the volume times G. Okay, density times the volume times the G. It's a little G that I forgot to include here. Right, so we find an expression for the volume. From this we have V equals the force over the density times G, giving us the volume of 2.5 times 10 to the minus 4 cubic meters. Okay, so if this is our volume, then we can go ahead and find the density of this solid. Okay, so we also know that the density of the solid equals the mass of the solid divided by the volume of the solid. All right, so we substitute the values. The mass was given, which is 237.5 times 10 to the minus 3 kgs divided by the volume, giving the density of the solid as 950 kilograms per cubic meters. Okay, so we go to the second part of the question, which requires us to find the density of another liquid in which the same solid would float with only 1/5 of its volume exposed above the liquid surface. Okay, so here this means that this means that 1/5 of this volume is exposed above the surface. Okay, meaning that the submerged volume is simply 4/5 times the original volume. Okay, which is 4/5 times the volume of this particular solid, giving the volume which is submerged as 2.0 times 10 and minus 4 cubic meters. All right, so we are saying that the density, or rather this volume which is submerged, is the same as the volume for the liquid that has been displaced. Therefore the density of the liquid multiplied by the volume, submerged volume, must equal to the density of the solid multiplied by the volume of the solid. Right, so from here we're able to obtain the expression for the density of the liquid. Okay, we simply substitute the values in there, and then we find the density of the liquid as 1187 kgs per cubic meters. Okay, so here there was nothing much to do as well. Right, okay, so for those having questions, you can always reach out. Questions concerning the tutorial sheet, of course, reach out on Telegram. I'll be able to assist you. Okay, so as you can see in the tutorial, I'm trying to be fast, okay, so that you don't have issues buying data to watch long videos. Right, so I'm trying to be fast so that the videos can be short and you can all have access to them. All right, okay, so let's go to the last question here. Let's go to the last question here. So the figure here shows the essential parts of a hydraulic brake system. The area of the piston in the master cylinder is 6.4 square centimeters, and that of the piston in the brake cylinder is 1.8 square centimeters. The coefficient of friction between the shoe and the wheel drum is 0.5. If the wheel has a radius of 34 centimeters, determine the frictional torque about the axle when the force of 44 newtons is exerted on the brake pedal. Okay, so we want to find the frictional torque here when this force is applied on the pedal. Okay, so it's like a wheel is rotating and then you apply brakes. Okay, so now we want to find the frictional force, the frictional torque. So this torque will be obtained from the force of friction, okay, in this system. Okay, so Pascal's principle here gives that the pressure in the piston 1 must equal the pressure of piston number 2. If we look at the system, we have two cylinders, rather. We have two cylinders. Okay, so if you apply force on the pedal there, the pressure in the master cylinder is going to be equal to the pressure in the brake cylinder there. So now we are saying let P1 be the pressure in the master cylinder and P2 be the pressure in the brake cylinder. Also, we know that the pressure is given us the force per unit area. So we can say that the pressure in cylinder 1 is equal to the pressure in cylinder 2. Okay? F1 over A1 is equal to F2 over A2. All right? So notice here that we want to know the force first that is applied in this brake cylinder. So the force applied to the master cylinder we know, which is 44 newtons divided by the area of the master cylinder equals the force applied on the brake cylinder divided by the area of the brake cylinder, right? Giving a force of 12.8 newtons. Okay, so this is the force that is applied on the brake cylinder. Okay, so notice that this force which is being applied on the brake cylinder is normal to the wheel drum. Okay, it's the force that is pushing the wheel, okay, normal to the wheel drum. Okay, so if this is the normal to the wheel drum, then we can find the friction force between the wheel drum and the shoe. Okay, so then we proceed. We are saying that the frictional force is equal to the coefficient multiplied by the normal force, which is 0.5 multiplied by the normal force we just obtained, which is F2, 12.8 newtons, from which we find our frictional force as 6.4 newtons. Okay, so now we can go ahead and find the torque resulting from this frictional force. We know that the torque is given us the force times the radius, in this case, which is our frictional force times the radius. Okay, 6.4 multiplied by the radius, which is 0.34, and we have our frictional torque as 2.1 newtons. Okay, so that's how you go about this. So just remember, we are finding the normal first by looking at Pascal's principle, knowing that the pressure in master cylinder is equal to the pressure in the brake cylinder. So from which we're able to obtain the force which is exerted on the brake cylinder, and that force is acting as the normal through the shoe. Okay, it's acting through the brake shoe as the normal to the wheel drum. Okay, from which we're able to obtain now the frictional force and finally the frictional torque. Okay, so this is the end of this tutorial. We'll meet in the next tutorial. Okay.